So the next thing I'd like to start with is looking at some special cases. So let me quickly draw here the general form of the capacity region, which is unknown in general, but of course in general it will have this shape, right? There's going to be some surface that represents the boundary of the capacity region, and everything inside that down to 0 in that front part there are points that are achievable. Of course, we're interested mainly in the surface points. And as a simple first step, let's try to figure out one of these points, namely this one. Where does that one lie? And it'll turn out that one's actually, if you look at the problem, one message, 2 separate channels, it looks pretty easy, right? I mean, it's all, or it looks, I think, relatively easy to do. In fact, it's not too hard to solve. This kind of problem is also known as a compound channel. So what is a compound channel? That's a case where, for example, suppose there are 2 channels and you don't know which one is going to happen, a py1 given x and a py2 given x, right? And you're trying to send a message to it's the same receiver, so let me call it yn if you like. It's the same decoder, but you don't know what the channel is in between. So there's maybe some, let me draw it as a switch maybe. There's a switch here, and this is yn, this is y1n, y2n. And then the decoder wants to decode the message, right? So this is sometimes known as compound channels. For instance, if you have a fading channel, you'll have like a continuum of these compound channels, right? And since we don't know which one is happening, but we still want to be able to decode both, that corresponds exactly to a broadcast channel with common message, because here the capacity region depends only on the marginals, right? So it's the same problem. So we solve compound channel problems is the same thing as broadcast channels with a common message, okay? So that relation is very close. So uncertain channels, uncertainty in channels. So what's the capacity here? Well, if we talk about coding, what's the natural code here? Well, it's just to use a plain old regular, code with x and w running from w equal or not, w naught, running from 1 to 2 to the nr naught, right? And suppose we do that. That's our code book. Encoding is obvious. Given the message, you just pick the code word out and send it. Decoder 1, given y1n, try to find a w naught hat such that x and w naught hat y1n is jointly typical with respect to p xy1, right? This will happen with high probability that you'll find such a typical pair that has high probability, because we've generated these IID, we've generated these IID, and they're related via the py1 given x channel. Okay, what can go wrong? One of the other code words might be jointly typical to do the union bound. What's the probability that a random choice is typical? It's just the to the minus n mutual information. Union bound, we just get what you'd expect, right? R naught has to be less than I x y1. Okay, and repeating the same arguments, we have this. Okay, so it's natural that we have the following bound, the min of both, and then we can maximize, right? So R naught max px min ixy1 ixy2 is achievable, right? That one's clearly achievable. Is that going to be the capacity? Well, we need to find a converse. So let's talk about that quickly, because there's one new element here. We have to make sure that whatever happens, we get some common answer. Because if you look here, you have the same x in both cases. So if we do the converse, What do we get? Okay, so let's start for the for reliable communications. We have R naught less than I of W naught hat 1, right? You know, plus da-da-da-da-dum, but I'd like to throw that out again, you know, Fanon's inequality, because that all just goes to 0, so I like to start with the end-to-end mutual information. We use data processing inequality as usual, and then a sequence of, just the usual sequence of steps. I equals 1 to n h of yi 1i given y 1i minus 1 minus h of y 1i given w naught y 1i minus 1, right? But w naught gives us x, so we can just stuff in here xi, and so this is just h of y 1i given xi, and here we can just say that's less than h of y1i, so here, as usual, you know, it's just the usual thing. We get I equals 1 to n I of xi y1i. Okay? Now, so we'll get the same thing with y2i. Okay, but we get this big sum. How do we convert it to a bound that's single letterized? Single letter? Well, we're going to have to generate something common here. So there's two ways of doing this. I'll show you one way. I don't know if I'll do the other. But let's see. What do we know about mutual information? It is concave, right, if the channel is fixed. So let's, you know, multiply and divide by n. So here we have an expectation. And what this concavity means, this is less than n I of x, let me call it bar, y1 bar, where p x bar y1 bar of x, let me call it ab. Well, what's the distribution of x? Well, the convexity, what we do is we average over all of them, right? So this is just going to be 1 over n I equals 1 to n p of xi yi a comma b. That's what this joint distribution in here is through the convexity, right? It's averaging the distribution. And this thing here, you know, use Bayes' rule to get pxi p y1i given x1i, but that one's independent of I, the channel, right? So here we'll just get 1 over n summation I equals 1 to n p xi of a. That's the new input distribution, p y given x. This is constant b given a, right? That's the joint distribution. Okay, we can do the same thing now for y2. We'll also get the same thing for y2. Should have written here n less than or equal to n I x bar y2. And fortunately, we'll get the same expression, right? So we'll also get this expression with the same x. So the important thing here is this x bar is the same as this x bar. And the channel is here py1 given x, and the channel here is py2 given x. We don't have to worry about the joint distribution, so indeed we've found that this is an upper bound, right? With just px replaced by x bar, right, is also an upper bound, right? And since those two are the same, since it's just a relabeling, we get the answer that this is indeed the capacity. This is this point up here. Okay, so why did I emphasize this? The important thing is we have to get two outer bounds, and we have to make sure that these random variables are common, you know, in both expressions. So this is always something we have to worry about later too. When we get multiple bounds, we always have to make sure we do some manipulation to make sure we get some kind of common variables that match exactly, you know, the constraints of the problem. That's just, it's not hard, but it's just important to realize. So this is one approach, is to use concavity. There's a second approach by using time-sharing random variables. Maybe I do quickly go over this because we see this trick all over the place. The second approach, which is effectively the same, goes like this. Instead of going here through concavity, we go here and we say, aha, also multiplied by 1 over n. But take a look. This here is the same as n times I of x t y1t given t, right? Where t is a random variable that takes on the value I with probability 1 over n for I equals 1 to n, right? It's the same thing, because now if I write this out, this is just an average over t, and that's just 1 over n. And then I condition on the value of t equals 1, t equals 2, and so on, right? So I can write this as equal to the given t. Okay, but now I have the problem, I have this t in here. This represents like a time sharing of some kind, which I could optimize in principle. Now to show that I get what I get, well, this isn't too hard, because here I can write h of y1t given t minus h of y1t given x1t t. And you can show from, if you choose this t, actually you get this Markov chain. So this is just h of y1t. You can easily see that once you write out the joint distribution, and this thing here is less than or equal to h of y1t. Right? And so this here is less than ni x1t y1t. And it turns out that this is just, the channel from here to here is just py1 given x. You can show that when you write out the joint distribution of all random variables. And then we're back here at this result. Okay, but they were quite different, right, the bounds. Here I used concavity of I, x, y when p, y given x is fixed. And here I used a time sharing trick, random variable. Now, this one is preferred, this method with time sharing, because it turns out, as we'll see later, sometimes you need a time sharing random variable. And so the concavity will a little bit mislead you, because you won't get the right bound. You'll get something that's too big, will sometimes happen. So the better approach is usually to keep explicitly those i's in here. After all, here, we can mix different distributions, and sometimes it turns out for networking problems, sometimes you should for some time use one pair of distributions and for another time another pair. We'll see examples of that happen. Okay, is it clear? What I did is just two different ways of proving something you'd expect, but they are important to understand that they play a role. Yeah?
How do we know when to use this kind of time sharing?
Oh, you always do, because we always wind up with an expression like this as a sum, always. So you can always apply time sharing to that, because we can always write a sum like this, always. So using time sharing for converses is a universal method. In fact, you should always use it, because then the next step is to try to get rid of it, like we just did here. But sometimes you can't get rid of it. And sometimes when you can't get rid of it, it means you need to use time sharing. So it's a fundamental trick that it needs to be in your bag of coding methods, which is, it's a simple method. I mean, there's nothing deep about it. You'll notice here too, we're viewing it as a random variable. So in the Elgamal-Kim book, this is sometimes called randomized time sharing. But it's never really important to randomize it. It's just a trick for the proof. You can always just, combine all, modes at one beginning and then at the end, and you can tell everyone what it is because we're conditioning on it. So randomization isn't really needed. In practice, you would never do it randomly. You would actually, assign a certain slot to something and another slot to something else, and then take appropriate averages, but in the right way, averaging in the right way. Okay, so that's why I say I prefer this trick, not the convexity trick. It's much more explicit, and it tells you something, and it's important to be careful how you get rid of this. We can do an example of this later when we get to the multiple access channel. You'll see that if we drop it, we get the wrong answer. If we keep it, we get the right answer. But it's always there. Okay, maybe do one quick example. First of all, what's important to realize, this is less than or equal to the minimum of the two capacities, right? So if the capacity C1 is the maximum of this, so of course if we take the maximum inside, we generally get something bigger, right? It's kind of obvious, but it's just important to realize. The only time it is equal to that is if the optimizing joint distribution is the same, then it happens, and maybe also if the two different ones, of course, give the same answer, and so on. But okay, so that's kind of clear, I think. Okay, so, right. The important thing then is the minimum. So one example of this is Gaussian channels. Let's suppose, for example, we'll do one quick example to already get some feel for this. Let's suppose y1 is x plus z1, where this here is Gaussian with variance sigma 1 squared, and y2 is x plus z2. Means 0 sigma 2 squared, and suppose sigma 1 squared is less than sigma 2 squared, right? So the second channel is noisier than the first. Suppose we have the usual power constraint, then clearly here, you know, this R naught, maximum R naught is just, obviously the maximizing distribution for x for both is going to be Gaussian. So we'll just get the minimum of C1 and C2, so here we'll get 1/2 log of 1 plus p by sigma 2 squared, unfortunately, right? So we're unfortunately limited by the worst channel, which makes sense because we're requiring all receivers to decode. So, you know, if this is a kind of situation where you might have, you know, you have your digital radios in your cars, you have to design for the worst case. Well, not necessarily, sometimes you just let it cut off, right? But you're designing for some threshold, and so you have to design for the worst case in that threshold to make sure everyone decodes. So your performance is dominated by the worst receiver. Let's then go to the next example where we do actually have, so no more common message. Now we have two individual messages. And we'll do this Marten coding thing and just see what kind of rates we get and talk a little bit about that. Okay, so the same setup, but now instead we're looking in this plane, right? So we're now decided, okay, this point we always have for any broadcast channel. In fact, we always can get this in general. So let's see if we stick into this plane, and it turns out the problem is still open in general inside even the plane where R0 is 0. But let's come up with a method, this Marten coding method, and just see what kind of, what does the region look like in that plane. Okay, so the coding is going to be done as follows. So we'll use the Slepian-Wolf coding method as we discussed, but let's choose, we have to choose some random variables with random variables and joint distribution P, U1, U2. Okay, so what we'll do is we'll put, we'll have code words U1, W1, so there's my first message, W1, V1, and code words U2 and W2, V2, right? So we're making the code, every message chooses a subset of code words, a set of code words. Message 2 chooses a set of code words, then we try to find a pair V1, V2 so that these are jointly typical. And we know, so if this here has rate R1 primed and this here has rate R2 primed, then we know by what we just did, we need to have R1 primed plus R2 primed bigger than I, U1, U2. Right? That's what we need. If we find that, we're successful. We found a jointly typical pair. What do we do now? Well, we have to transmit an x, so we're going to choose a function. You know, so we choose function, choose a function which maps U1 cross U2 into x, and we send xi equals f of u 1i, u 2i, all I. Okay, that's what we transmit down the channel. So that's our coding method. And we have already a first, constraint that we will have on the rates. So it's kind of weird, right? This constraint has to do with an error probability at the encoder. This sounds a little weird, right? And it is weird because we don't really have an error probability at the encoder. In principle, the encoder can just look in every bin and see is there a jointly typical pair or not, right? And if there's more than one, and there will be if we're big enough, just choose one of them and we'll agree with the receiver ahead of time which one we chose in every subset, right? So there is no, the transmitter can check whether the code book is problematic or not, and if it is problematic, he can always fix it, right? That's the main point I want to make with this. And if there's more than one jointly typical pair in every subset, you agree ahead of time with the receiver which one you choose. Now, how you make that choice is an interesting question, because some proofs will only go through if you choose it randomly, or with some probability distribution, which corresponds to the sequences you have there. That's an important point for secrecy. So it turns out for secrecy, you sometimes have to be very careful how you're making these choices. And so there's a nice, so Paul Cuff had a nice idea, something called a likelihood encoder, which carefully chooses these points with some probability distribution, and that makes ensuring secrecy possible. So there all these aspects you have to think about carefully when you do the proofs, because some proofs go through with only if you do things the right way. Especially with secrecy, you have to be careful. Anyway, so that's the transmission. What about decoder 1? That's left, right? Decoder 1. Well, just do the natural thing. Given y1n, try to find a pair. W1 hat, B1 hat. So what decoder 1 will do is it'll only try to decode what it's interested in, but also the binning point. So we could try to come up with something where it's only decoding this in a maximum likelihood way and considering the V1s to be random in some way, but turns out the rates we get for both are the same. But anyway, we're just looking for a pair U1n, W1 hat, V1 hat, Y1, little y1n. I could have written that small too, but whatever. Pu y1, right? And okay, since everything is jointly typical, right? By this step, U1, U2n are jointly typical with respect to the joint distribution. A function always keeps things jointly typical. That doesn't change typicality. Once it goes through the channel, everything is jointly typical, right? So the actual transmitted W1 and B1 will be jointly typical with YN. That's good. We need that, otherwise we won't decode correctly. Now the only question remaining is what can go wrong? Well, one of the others may have been jointly typical. So now we have to be a little careful because some of the pairs that we're choosing have the same W1, but still all of them were chosen at random, right? So it doesn't really matter. So how many of these do we have? 2 to the power of nr1 plus times 2 to the power of nr1 prime. And the probability that 2 independent values happen to be jointly typical is 2 to the minus n mutual information between u and y1. So the rate constraint becomes r1 plus r1 prime less than IUY1. So it's kind of the straightforward one, and same at decoder 2. We get the constraint R2 plus R2 primed U2Y2. Okay, and so those are our 3 bounds we get. This is the bound where we give up some rate to make the U's correlated. If we chose the U's to be independent, it's also a natural approach, then we wouldn't pay a rate price here. However, it'll turn out then these numbers in general get lower, right? So having U1 and U2 correlated can help raise these, but we do pay a price for it. So the question is, what is the right trade-off, right? So Sometimes the trade-off might be, well, don't even make them correlated at all. That would be nice, because then we have a much easier encoder structure, right? This encoding operation is actually, it's not so easy to build. We'll mention one way to simplify it in a moment, but for the moment, let's just consider this. Okay? So putting these rate bounds together, we again want to use Fourier-Motzkin elimination to get rid of the extraneous rates, and putting it all together, it's not very hard because it's really easy here, right? So what we'll get is the resulting rate region. So this is sometimes called Marten's region for the broadcast channel. The rate bounds look like this: 0 less than R1 less than or equal to I U1 Y1, 0 less than R2 less than or equal to I U2 Y2, and R1 plus R2, so we're going to get a sum rate bound, which is just the sum of these two, U1 Y1 plus I of U2 Y2, but minus this price we're paying, minus I U1 U2. So it's really easy to check that the Fourier-Motzkin elimination will give you this, right? Let's give this region a name. So let's look at all the rate pairs R1, R2, such that these inequalities are satisfied. We'll call R as called M for Marten, and what we'll have is U1, U2, and some F. So maybe I'll write it as a triple. PU1, U2X is just this set. And what I also want in here is just to keep it clear, U1, U2, X, Y1, Y2 has to form a Markov chain. So this chain is Markov, right? That chain has to be Markov. Okay, so but I can still optimize. Now I can still optimize over all joint distributions of U1, U2, and X. And that then becomes Marten region. So maybe I should write it like this: RMU, and RM is then the union over all PU1, U2X of RM PU1, U2X. Right, so that will be the Marten region. So we still want to do an optimization. So let's draw this, let's draw every one of these subregions, and then talk about what the union looks like. Right, so if we look in this plane, the region looks like this. Okay, it's every region, for every choice of joint distribution U1, U2 and function to X, or for every triple joint distribution, we're going to get a pentagon. Here we'll have I U2 Y2. Here we'll have I of U1 Y1. And then these go up. They would meet here, except for that subtractive term, which takes out something, and so we get this bound here. And this point here is, of course, that sum minus that. So this becomes I of U2 Y2 minus I of U1 U2, right? And this point here similarly becomes I U1 of Y1 minus I U1 U2. I guess I did this wrong, U2, Y2, my apologies. U1, Y1, of course, right? U1, Y1, U2, Y2. And now this is for a fixed joint distribution. If we change the joint distributions, we might get a region that looks like, this. This might be the RM, because we get a lot of these pentagons, right? And then the outer shell of them becomes this. This here will be RM PU1 U2 X fixed. Okay, so then that's what we want, and that's how we generate like some achievable rate in here. We don't know if this is optimal, so we might get some set of points in the plane that might look like this, but might be strictly inside the ultimate boundary, which we don't know what it is. Right, the capacity boundary. This will be in the blue line in the plane, but inside. Okay, that's this orange curve here. Maybe it is the boundary. We don't know. For some problems it is. We'll do some examples. Okay, any questions about that? Okay, now what's going to be interesting for us as a next step is the following. Let's look at the corner points. These are really always interesting, these corner points. Let's choose this one. And let's look at that rate pair, right? One is u2, y2. One is iu1, y1 minus iu1, y2. Now if you look at this, this should remind you of something. That rate. Suppose u2 was a state, then here I would have iuy minus ius. We've seen that before with the Gelfand-Pinsker problem. In fact, the coding is exactly the same because here I'm not doing any kind of subcode approach for u2. u2 is just a code word all by itself. So in fact, the way to think about this is in the following kind of architecture to approach this corner point. It goes like this. We take W2 and we encode it into just a regular code book. It might be LDPC code plus modulation. And then we're getting something that we view as interference. Right? Let's say U2 N. So this will be our encoder 2. And now what we're going to do is we're going to treat this U2 as if it was state. Now, and it's more or less IID, you know, with the probability distribution PU2. So if we treat that as a state, how did we do the encoding? Well, we'll apply a Gelfand-Pinsker code here and use that for our W1. And then we'll get some intermediate x1n, which we would be transmitting for the Gelfand-Pinsker problem. But of course, we now have to combine these two in some kind of function. Say x1n, u2n. I guess maybe I can call this u1n instead of x1n. I used x just to match to the Gelfand-Pinsker problem, but I can use u1. Then the picture matches to get xn. Okay, so that's the architecture. And so now you see why knowing the state ahead of time was useful. Remember, I tried to emphasize, you know, okay, it seems weird that we would know the state non-causally, but here we do because the messages are available ahead of time. So you can do this encoding ahead of time or instantaneously for a very fast processor, and then use that treat it as interference, which could be really big, right? The power of this could be much higher than the power of this. And yet we know if things are Gaussian here, so if this was Gaussian, this was Gaussian, the remaining channel was Gaussian, we know we can even get rid of this interference completely, which is interesting, right? And that's where the dirty paper coding ideas come in for Gaussian broadcast channels. So we'll look at those things explicitly yet. But then we get exactly this rate for user 1, right? It's exactly the rate of the channel that effectively, well, I guess I should be careful. This is x1n. There's a u1 here internally, right? Remember what we did? This should be x1n. So let me take that back, because remember how Gelfand-Pinsker code was done? We generate a u1 inside, and then we use u2 and u1 to generate an x1. So it's possible I could just say we're generating it directly. So maybe x1n here just is xn. Maybe that's one way to look at this. So I guess I could view it as this architecture directly. There's different ways of looking at this, but anyway, let me just do it that way then, perhaps. The other one was more accurate, right? The u1n I generate internally. Maybe I should just leave it. Let's just leave it at that. So apologize for erasing so much, but let me just view it as this, after all, as u1n. I think in my notes I have it with the x1n, but now I guess I have the feeling I should just use u1n after all, right? The u1n is sort of internally generated, right? Okay, but then we just add them up to get the x1n, because this is the state and the u, and get the x, right? And then we get exactly this rate. And that's how we can approach that corner point. To approach this corner point, we just flip this around, right? We encode U1 and then do the Gelfand-Pinsker code against the interference of the other users. So we get two approaches, one for getting this corner point and the other one for getting this corner point, and in principle we can get everything in between by time sharing, right? So in fact, the design of these Marten codes, kind of, if the simplest kind of Marten code is one that's actually Gelfand-Pinsker code. So you might want to start there. And that's why there's interest in understanding the Gelfand-Pinsker problem with non-causal state as a first step, right? Because it corresponds to a broadcast channel where we try to approach those corner points. Okay, so let's do one example of a channel, broadcast channel, where this is the capacity region. It's not going to be too difficult, but even though it's not difficult, once we have the answer, the following problem took many years to solve because people didn't have this coding technique yet. So they tried the superposition and somehow they couldn't prove that they got capacity and they didn't know what to do. And then once this paper came out, the problem became super simple. The whole solution.
Better than time sharing between those 2 points?
Sorry?
Can you do better than time sharing? Is it
well, it depends. For some problems, so for some problems, yes, because this method isn't yet the best known method. The best known coding method for broadcast channels combines this with superposition coding, and I haven't yet talked about superposition coding. So that's the next thing I want to talk about. So the largest known rate region, you have to do this stuff on top of something. There's some results that show that you can choose either to do superposition or this method, and that's good enough. But we do need the superposition method yet. So this method isn't always the best. That's the main point, which already makes it even more interesting, to understand what's going on here, right? That's why it's not clear whether we really even have the best coding method yet for broadcast channels. It's not obvious. There could be better methods. And that would be really fascinating. It's usually much more exciting to get new constructive methods than proving new converse bounds. I mean, converse bounds, you're kind of showing, well, you're solving a problem, that's great, but you haven't constructed something new. Whereas new coding method, that's important. That's really important, right?
Sir,
yeah.
In the time sharing, one user will send for certain amount of time, and another user will send for the rest of the time.
No, what I mean by time sharing here is something a little different. I mean, we operate at this point for part of the time and at this point for another part of the time. And then the rates are just the average. So I don't mean, so when I say time sharing, I don't mean only one user is transmitting. We're not only transmitting to one user and then some other time to another. I mean, we're using two different modes of operation and sharing those over time.
So we are simultaneously transmitting
yes.
the coded signal and...
That's right. So for example, if we half the time, send to both at this rate pair, half the time this rate pair will land right in the middle, right? So we'll always get points on the line.
Because of that, we are getting this.
Yes, you can get any point on the slope, yeah. So time sharing is a classic technique. When we get to multiple access channels, I'll get into this in a little bit more detail. One disadvantage of time sharing is the delay, right? So to operate reliable here, I already need long codes. To operate reliable here, I need another set of long codes. And then to operate in the middle, I double the delay, right? So I have twice as long coding I have to worry about. And if you have now more than two receivers, like 3 or 4 or up to 8, well, now you're really making the delay long because you're averaging over many kind of modes of operation, and that's not something you may like to do. In fact, if I have 3 users, I have many different orders I can do this, and I can do 1, 2, 3, or 2, 1, 3, or 2, 3, 1. So I have 6 orders, so there's 6 different things I have to time share, and so now I'm blowing up the delay. Now, in information theory, I'm ignoring delay always. Now I'm saying delay is a problem, but in practice, this time sharing isn't always so necessarily the thing you want to use. That's why, for delay reasons. So the main point I want to make with that, we'll sometimes be interested in other methods to get points here on the boundary. And I'll discuss some of those for the MAC, for the multiple access channel. That's not so much an issue here, but for the multiple access channel, it leads to interesting questions and very practical questions. Very practical questions.
Sir, you said that we don't know this is optimal or not.
No. Yeah.
But if we apply the time sharing,
yeah.
like for so that would would not be an optimal technique.
Well, it may not be. I mean, here I'm just, so if I do time sharing between these two, I just get this pentagon. But the pentagon may not be optimal. So it doesn't have to do with time sharing. I mean, you should always consider time sharing, but yeah, it doesn't mean you're best when you do that. Okay. So let's do one example. And it sounds simple enough. Namely, these are called deterministic broadcast channels. Broadcast channels often we write as a shorthand with BC. So the model looks like this. Y1 is some function of x, and y2 is some function of x, a different function. And that's it, right? So it sounds like a simple model, right? There's no noise. However, there might be some weird interference depending on how these functions are, right? From the transmitter perspective. And so when Tom Cover came up with his broadcast channel paper, there was a lot of excitement. People started studying it, and especially the more mathematically minded folks thought, okay, we'll look at some simple examples and see what happens, right? And so they looked at a particular model called the Blackwell Channel, which had this form. So it was a deterministic channel. There were papers, a whole bunch of papers. Edward van der Meulen applied superposition coding. Then they were trying to find converse bounds, and they just couldn't get them to match, right? Because everyone figured, well, we should be able to solve problems like this, right? But it turned out none of the tools worked. Once this theory came up, let's see what happens. So there's going to be a natural choice now for U1 and U2. And what we'll do is we'll choose U1 equals Y1 and U2 equals Y2. Okay, first of all, we have to ask, are we allowed to make that choice, right? Remember, we have to have a Markov chain U2 X Y1 Y2, right? That has to be Markov chain. So by choosing U1 Y1, it seems like we're breaking the Markov chain. Are we? Well, the answer is no. Why is that? Because these are functions. And now I can put functions on either side, I'll still have a Markov chain, right? Because given x, if I have y1 here and y1 here, I'm still breaking the dependence. So for deterministic broadcast channels, I can actually make the choice that I choose U1 to be the actual output sequence. I can control, after all, I can control through x the output sequence exactly. And I can do this through this coding method. And so now let's just plug it into the rate region and see what happens. So the Markov chain is okay, so I'm allowed to make this choice, permitted, because y1, y2, x, y1, y2 is Markov. And if there was noise, of course, this wouldn't be a Markov chain, right? I mean, if there was noise here, then well, you can't say given x, y1 and y1 are statistically independent. But here, given x, y1 and y1 aren't statistically independent because they're completely determined. So it only works in this case. But it's a nice case because it shows you controlling the outputs kind of makes sense here. Yeah, let's just plug it in. So we'll get R1 less than I of y1, y1. What is I, y1, y1? It's just the entropy. R2 is less than the entropy. And R1 plus R2 is less than or equal to, let's see, it's the entropy of y1 plus the entropy of y2 minus the mutual information between y1 and y2. And that's just the joint entropy of y1, y2. Okay, that's the region. And now, so what we'll do is we'll get a region like this, and then we still have to optimize over the joint distributions, and we'll get a curvy region. Turns out this is the capacity region. And it's not too hard to show. It's basically a cut set argument that shows that this is the capacity region. So in particular, we can do a cut set argument here. So what we can show that is the following kind of bound. So it's the cut set bound for the broadcast channel, outer bound. So this is, maybe I can just do it. So a general outer bound on the broadcast channel is the cut set bound. It looks like this. C has to be a subset of the union over all joint distribution, over all distributions on Px of 0 less than or equal to R1 less than or equal to I, R0 plus R1, I x y1, 0 less, let's drop the 0. These are all just positive rates. Let's not, I guess, be too, let's not worry about the negative rates. And R0 plus R1 plus R2 less than or equal to I x y1 y2. Okay. So if you think of this as, it's kind of like having 3 cuts, right? Because here I have node 1, here I have node 2, here I have node 3. There's a cut here, there's a cut there, and there's a cut here. This cut is the last one, right? This cut here is to receiver 1. I guess maybe I should call this 0, 1, 2. So this cut here corresponds to this bound, that the everything going to user 1 is upper bounded by the mutual information from here to here, given what this guy knows, which is nothing. But anyway, this is an outer bound on the capacity. And the point is, we can prove that in a moment, but the point is because y1 is a function of x, this is just h of y1 minus h of y1 given x, which is h of y1, h of y2, h of y1, y2, right? So we get exactly this form here, okay? So this turns out to be capacity of deterministic broadcast channels. So once you have this region, the finding capacity of any deterministic channel is easy, and the problem that most of these people were working with was the Blackwell channel, which was a special deterministic channel, and suddenly they could solve it. And it became even a really simple solution. That's quite remarkable, you know, and that took several years, right? There were a whole bunch of, a string of papers trying to come up with coding methods, trying to understand what to do, and suddenly, boom, the solution gets easy, right? So that's what, of course, research should do, is to, you know, do that. So anyway, for any deterministic broadcast channel, we have the solution, and it's even really nice. We just can control the outputs any way we want. That also tells you that this method is very good for channels with little noise, with low noise, right? Because the noise shouldn't change this too much. So if we have very low noise, maybe what we should do is kind of control the noise-free versions completely. And then if there's additive noise, for example, we can control, and then we'll just lose a little bit because due to how much noise there is. So we're virtually optimal at low noise for channels where we have additive noise on certain deterministic outputs, right? So for example, if this was a big base station with lots of antennas, you have your mobile devices, each of them has a whole bunch of antennas, and if the noise is very small, maybe we should just, maybe this coding is really good because we must be really close to the boundary because the only amount we have to back off is due to the noise in some way. And that insight is actually very interesting, right? Because it gives you other ways of coding just for the deterministic part. How do we do that usually for broadcast channels? We use pre-coding, right? To get rid of interference. So if you ignore the noise, how do you get rid of interference? You usually just use inverse filters. And it turns out that works really well in practice. So almost all base stations that are sophisticated that are built today use just linear pre-coding because that is the best thing to do for the noise-free case. And the amount you lose, it just depends. You'll lose something due to the noise, but not much if the noise is small. Of course, once the noise gets large, you know, or you're around 0 dB or something, then this method may not be so good anymore. But we still use it anyway, right? But we know that inverse precoding is pretty lousy because of noise enhancement, so usually you start adjusting it. Anyway, like the simple things I think are very useful to contemplate from this perspective, right? Yeah, any questions about that? So, nice example. I like that very much. Let's see here. So what's next? The next thing would be superposition coding. Or I could just complete this cut set argument, and then I have to, let me do that first. That way at least I complete this. Let's just prove this cut set bound quickly. Let's prove that it's an outer bound. Let's start with the first one. So now we're in the full situation where we have all messages. Okay, so let's start with the first one. So for reliable communications, so error probability very small. The end-to-end mutual information has to be small, so that this, we get the following bound. N R0 plus R1 is going to be less than I of W0, W1, and the first channel output here. Okay, I could write the estimates, but let me just write it like that. And then it should be pretty easy to see that we're just going to get to this almost automatically. The only thing we need is we'll do the following. So this is the usual trick. We stuff in W2 here. Yeah, I may as well do that. Stuff in, well, I could. Actually, let me do it in a different way. I won't stuff it in after all. Let me just write this as a chain rule, right? H of y1i given y1i minus 1 minus h of y1i given w0, w1. It's even easier, right? This one here is less than or equal to h of y1i. This one here is going to be greater than if I stuff in the x, right? So if I stuff in xi here, I'll just get something smaller. And if I stuff in x1i, I can get rid of the others due to the Markov chain, right? So we'll just get that. And this is then less than this sum. And you'll see I have exactly the form I'm looking for. And now I use my trick, right? This is n times I, x1 time sharing y, x time sharing, there shouldn't be an x1, xi, y1 time sharing given the time sharing random variable. But now I can get rid of that time sharing random variable the same way I did before. I'll get xt, y1t, right? Same steps, so I get that here. I'd get the same thing here with xt, y2t, and I can repeat the whole thing here with all three messages here, and then just get xt, y1t, y2t. It's all the same, so that way you get this cut set bound. Yeah, but the form is very natural. Once you get used to this stuff, I mean, this is really natural. And this cut set bound exactly matches the achievable Marten's region, because there y1 is a function of x. So we just get entropy here, entropy, and entropy, and the two regions match exactly, and that gives us the proof. But this is a general outer bound. This is a general outer bound on the region, so it gives us, for example, a curve that looks like this, and curves that look like this. Right, here it'll meet, because we've already seen that the cut set bound matches there. In fact, if we do that, so if we drop all the rates, we'll just get these three bounds. And you see it's the minimum of these two, the capacity region. This one here is, if I drop this one I can drop, because this is bigger than that, and that's bigger than that, and so R0 is less than the minimum of the two. So this cut set bound is exactly gives us that point. It's just the same bound. Okay, so we do have, an outer bound. We have these inner bounds based on this coding techniques, and we try to make them meet. We discover this isn't good enough yet. So what I'd like to do after lunch, and maybe it makes sense to already go there, is after lunch I'll talk about a superposition coding, which is the second main method of coding that we know of. So the main methods are, well, basic Shannon random coding, then there's this binning stuff, and there's superposition coding. And those methods are basically all we have, other than this compute and forward stuff that got more attention recently, and that's it. So that's all the general methods we have today. But we do need to talk about superposition coding. And we'll do that after lunch. So, are there any questions right now?
So there, why X came in?
Which one? Oh, why it came in? Oh, just as a bound. You know, so I went a little fast. Right, you'll agree with that. I mean, conditioning can't increase entropy, and then because, you know, there's this is just a noisy version of that, I can just drop this, right? And there's no feedback or anything, so this just goes away. We have a Markov chain. That's where it comes from. Yeah. Okay, so then let's go for lunch, and then we'll start again at 3 o'clock.